Could black holes be the place where physics finally breaks down completely? Not just bends, not just stretches, actually breaks. I think so, and I've spent decades trying to understand why. Black holes are the most extreme objects in the known universe, and for a very long time, even the greatest physicists in the world hoped they didn't exist. Not because they were uninteresting, exactly the opposite, because they were too interesting, because they demanded that we confront things about the universe that we were not prepared to confront. I'm Leonard Susskind, and I want to tell you what black holes are really hiding. Not just what they are, what they're hiding about the deepest structure of reality itself. Let me start with what a black hole actually is. The simplest description is this: a region of space from which even light cannot escape. That's it. That's the core idea. And it's an old idea, much older than Einstein. Back in the 1780s, two mathematicians working independently had essentially the same thought, an English clergyman named Mitchell and the great French mathematician Laplace. They were both thinking about escape velocity, the speed you need to travel to completely break free from a gravitational pull. For Earth, that's about 11 kilometers per second. Fast. But for a massive enough object, that escape velocity keeps growing, and Mitchell and Laplace both asked the same question. What if you built something so massive, so dense, that the escape velocity exceeded the speed of light? Then nothing could escape, not even light itself. You'd have a dark star, an object so gravitationally powerful that it was effectively invisible. Now, their calculations were based on Newtonian physics. They were wrong in the details, but the core intuition was right, and it was extraordinary for the 1780s. Then came Einstein. In 1915, his general theory of relativity replaced Newton's picture of gravity entirely, and it turned out that black holes exist in Einstein's theory too. Just 1 year after Einstein published his equations, a physicist named Carl Schwarzschild found an exact solution, a precise mathematical description of how space and time behave around a perfectly spherical mass. He was working on the Eastern Front during the First World War when he did this, and he sent his solution to Einstein from the trenches. Einstein was astonished. The mathematics was perfect. The solution described something extraordinary, a region of space so warped, so distorted, that geometry itself broke down at the center. But here's the thing. Even Einstein wasn't sure these objects could actually exist in nature. The mathematics said they could. Nature seemed too sensible to allow it. That attitude persisted for decades. Even into the 1960s, many of the greatest physicists in the world thought black holes were a mathematical curiosity, not a physical reality. The distinguished physicist Arthur Eddington, a colleague of Einstein's, very proper, very English, said simply that nature would prevent such absurdities from existing. That's it. Just a flat declaration. Nature won't do this. Well, nature does this. We know now, beyond any reasonable doubt, that black holes exist. They form when massive stars reach the end of their lives and collapse under their own gravity. They exist at the centers of virtually every large galaxy, including our own. In 2019, we imaged one directly for the first time, a shadow the size of a solar system surrounded by a glowing ring of superheated matter. The absurdity that Eddington refused to believe, real, sitting there in the sky. But accepting that black holes exist only brings you to the beginning of the real problem, because now you have to face what they mean, and what they mean is deeply disturbing. In Einstein's general relativity, a black hole has an event horizon. Think of it as a boundary in space, a sphere of no return. If you cross it, even traveling at the speed of light, you cannot get back. From the outside, the event horizon looks peculiar. If you watch an astronaut falling toward a black hole, you would see something strange. Their time would slow down, slower and slower as they approach the horizon. And right at the horizon, from your external perspective, their time would appear to stop completely. They would seem frozen there forever. That confused physicists for years. They thought it meant something impossible was happening, that stars couldn't actually collapse all the way. But the confusion came from forgetting something crucial about relativity. Time is relative. From the astronaut's own perspective, nothing unusual happens at the horizon. Their watch ticks at 1 second per second. They cross the horizon and continue falling. For a large enough black hole, they might not even notice the moment they cross it. Time stopping is a feature of the external view, not the internal experience. Both can be true simultaneously. That's relativity. Two perspectives, both valid, and neither wrong. So what's really at the center? Here's where the physics genuinely breaks down. In pure general relativity, the center of a black hole is called a singularity, an infinitely dense point where the equations produce nonsensical answers, infinities. But here's what's strange. The singularity is not really a place in space. If you look at the mathematics carefully, at the full geometric picture of what a black hole looks like, the singularity is a moment in time, the end of time. Space and time swap roles inside a black hole. What was a spatial direction toward the center becomes a temporal direction toward the future, and the future inside a black hole ends at the singularity. You don't hit a point, you hit a moment beyond which time does not continue. That is what general relativity predicts at the center of a black hole, and general relativity has no idea what to do with it. The theory breaks down entirely. It produces infinities and stops working. And we've known for decades that understanding the singularity requires something beyond general relativity, a quantum theory of gravity, a deeper theory of how space and time work at the smallest scales. But for a long time, physicists thought that the singularity was safely hidden inside the black hole, inaccessible, perhaps a mystery forever. And then Stephen Hawking changed everything. In the mid-1970s, Hawking did something nobody expected. He applied quantum mechanics to the region near the event horizon of a black hole, not inside, near the horizon from the outside, and what he found was astonishing. Black holes glow. They emit radiation. They have a temperature. These objects that we defined as things from which nothing escapes, they're actually radiating particles into the universe. Slowly, incredibly slowly for large black holes, but radiating nonetheless. This is Hawking radiation. And the picture Hawking used to describe it, while not mathematically complete, gives you an intuition for what's happening. In quantum mechanics, empty space is not actually empty. The vacuum seethes with activity, pairs of particles constantly appearing and annihilating in tiny fractions of a second, everywhere in space, all the time. Near the event horizon of a black hole, something unusual can happen. One particle of such a pair can fall across the horizon into the black hole. The other escapes into the universe. The escaping particle carries energy away from the black hole. The black hole loses mass. Over an incomprehensibly long time, the black hole slowly shrinks, and eventually it evaporates completely. Gone. That's the picture. Beautiful, disturbing, and the source of the deepest problem in theoretical physics. Because here's the question Hawking's calculation immediately raised. What happened to everything that fell in? Over the entire lifetime of the black hole, everything that ever crossed the horizon, stars, gas, light, information, all of it went into the singularity, that mysterious end of time, and the black hole radiated away its energy as Hawking radiation, and then it was gone. So where did the information go? Now, why does information matter? Here's why. Take anything. A book, a chair, a star. Destroy it completely. Incinerate it. Explode it. In principle, according to every law of physics we know, if you could collect every particle, every quantum of radiation that the destruction produced, you could reconstruct the original. Information is conserved. That's not a philosophical preference. It's a mathematical consequence of quantum mechanics. The fundamental equations are reversible. The past can always be reconstructed from the present in principle. Information cannot be created or destroyed. That's the law, and Hawking's calculation said that black holes violate it, that when a black hole evaporates, the information about everything that fell in is gone, not scrambled, not hidden, gone, destroyed, forever. This became known as the black hole information paradox, and it was not a minor technical puzzle. It was a direct contradiction between the two greatest theories in physics, general relativity and quantum mechanics. One of them had to be wrong, or both, or we were missing something fundamental about the nature of reality. I spent years on this problem, so did many of the best physicists of my generation, and I believe the resolution is that information is not destroyed, that it comes out, encoded in the Hawking radiation in a form so scrambled, so complex that it is practically unreadable. But there, in principle, every bit of information that ever fell into the black hole is present in the outgoing radiation, just scrambled beyond any conceivable practical ability to decode. The black hole is not an eraser, it's a scrambler, the most powerful scrambler in the universe, but a scrambler, not a destroyer. The information survives. That conclusion, which is now broadly accepted in the physics community, required a revolution and in how we think about space and time. It led to the holographic principle, the idea that the information content of any region of space is encoded on its boundary surface, not its volume, its surface, three-dimensional reality described by two-dimensional information. It led to the ADS-CFT correspondence, one of the most profound discoveries in theoretical physics of the last 30 years. The demonstration that a quantum theory with no gravity living on a boundary can give rise to an entire higher dimensional space-time with gravity in the interior, space-time itself emerging from quantum information. All of that came from black holes, from taking seriously the paradoxes they pose, from refusing to say that the problems would simply resolve themselves. Black holes didn't just break physics. They pointed the way toward a deeper physics, a physics where space-time is not fundamental, where gravity is not fundamental, where everything we think of as the basic fabric of reality emerges from something more abstract, more quantum, more informational, and we're still working it out. The information paradox is mostly resolved, but mostly is not completely. The nature of the singularity remains mysterious. The full quantum theory of gravity remains out of reach. Black holes are still hiding something deep, something that will require the next revolution in physics to uncover. And that's exactly why I find them so fascinating. After 50 years of thinking about them, black holes are still the place where our best understanding of the universe simply runs out. And what's just beyond that edge is the most interesting question in physics. What lies beyond the end of time? What happens when space and time themselves break down? And what the universe looks like from the other side of a black hole, we don't know yet, but I think we're getting closer. And when we find out, it will change everything.